All right, let's get right into it. We're going to tackle one of the big, kind of weird questions in calculus. If you keep adding numbers together forever, an infinite number of them, does that sum just blow up to infinity? Or can it actually land on a real finite number? It's a fantastic puzzle, so let's jump in.
I mean, it just sounds wrong, doesn't it? How can you add infinitely many positive numbers and not get infinity? Well, that's the paradox we're going to unravel today by looking at something called infinite series and the seriously cool tools we have to figure them out.
And to really get our hands dirty, we're going to start with a super famous and honestly a pretty sneaky series. It's called the harmonic series, and it is the perfect place to start this investigation.
So take a look at this. You're adding 1 plus a half plus a third, a quarter, and so on. You can see the pieces you're adding are getting smaller and smaller, right? They're racing towards zero. So your gut is probably telling you, hey, this has got to settle down somewhere. It has to converge. But here's the spoiler. It doesn't. And we're about to see this brilliant visual proof that shows exactly why it shoots off to infinity.
You know, the trick to cracking this whole thing is to change how you look at it. We need to stop thinking of it as just a sum of numbers and start picturing it as a collection of areas. Seriously, this one little shift in perspective, it changes everything.
So how in the world do we do that? Well, we take our series, which is a discrete sum of individual terms, and we find its continuous counterpart. In this case, the function f of x equals 1 over x. This is the move. This is our bridge from the world of sums into the world of geometry and areas.
Okay, so picture this. We can draw each term of our series as a rectangle. Let's make it easy on ourselves and say the width of every single rectangle is just 1. That means the height is the value of the term itself. So the first rectangle has a height of 1, the next a height of 1/2, then 1/3, and so on. Now if you add up the areas of all those rectangles, what do you get? You get the exact sum of our original series.
And right here, this is the light bulb moment. If you sketch the curve f of x equals 1 over x right underneath all those rectangles, you can see with your own eyes that the corners of the rectangles are sticking out over the top of the curve. It's so simple, but it's a rock-solid proof that the total area of those rectangles has to be bigger than the area under that curve.
So let's just lay it out side by side. On one hand, we have the sum of the series, which is just the total area of all our rectangles. On the other hand, we have the integral, which is the area under the curve, and the visual makes it undeniable. The sum is greater than the integral.
And here comes the knockout punch. We already know from studying improper integrals that the area under the curve 1 over x, from 1 all the way to infinity, is infinite. So let's think about this. If our series, the area of those rectangles, is even bigger than an infinite area, well, what else can it be? It has to be infinite too. And just like that, we've proved the harmonic series diverges.
Now this whole rectangle trick isn't just a one-hit wonder for the harmonic series. It's actually the entire idea behind a super powerful formal tool, and we call this tool the integral test.
So the integral test basically just takes that visual logic and turns it into a rule. It says, hey, if you've got a series and you can find a function that lines up with its terms, then that series and the integral of that function, they're linked. They share the same destiny. If one converges, the other converges. If one diverges, the other one does too.
Now hold on, there are a few conditions, a little checklist you have to run through first. For this whole comparison to be valid, the function you pick has to be positive. It has to be continuous, so no gaps or jumps, and it has to be decreasing. As long as those 3 things are true, you're good to go. You have a green light to use the test.
And the outcome is just beautifully straightforward. You calculate the integral. If you get a finite number, meaning the integral converges, then you know for a fact your series also converges. If you calculate the integral and it blows up to infinity, meaning it diverges, then you know your series also diverges. It's a perfect two-way street.
Okay, and this is probably the most important warning I can give you. This is the trap that almost everyone falls into at some point. The integral test tells you if the series converges, but it absolutely does not tell you what it converges to. The value of the integral is not the sum of the series. Just remember those little corners of the rectangle sticking out. That's your visual proof that the two values aren't the same. This test is only about behavior, not the final number.
So the integral test is awesome. But let's be real, sometimes calculating those improper integrals is a pain. So what if I told you there's a huge shortcut for an entire class of series? Allow me to introduce you to what is about to become your new best friend in calculus.
This is the p-series test, and it's a game changer for any series that looks like 1 divided by n raised to some power, which we call p. And the beauty of it is that p is the only thing you need to look at. Just that one little number tells you the entire story.
And here they are. The rules, it is this easy. If that power, p, is bigger than 1, the series converges. End of story. If p is less than or equal to 1, the series diverges. That's it. And think about it. The harmonic series we started with is just a p-series where p equals 1, which fits our rule perfectly for why it diverges.
All right, that's enough talk. Let's get these new tools off the shelf and put them to work on a couple of real examples so you can see just how powerful and efficient they are.
Okay, first one up, the sum of 1 over the square root of n. So, step 1, you spot the form. This is totally a p-series. Let's just rewrite that square root as n to the power of 1/2. Okay, so our p is 1/2. Now we check our rule. Is 1/2 greater than 1, or is it less than or equal to 1? It's less, so the series diverges. Boom, done. Took, what, 10 seconds?
Okay, now for one that isn't a nice, neat p-series. We've got the sum of 1 over n times the natural log of n. This thing is practically begging for the integral test. So our function is f of x equals 1 over x ln x. We quickly check our 3 conditions. Yep, it's positive, continuous, and decreasing once we get past x equals 2. So we set up the integral. This one needs a quick u substitution, and what we find is that the integral goes to infinity. So what's our conclusion? The integral diverges, so our series has to diverge too.
So there you have it. We've just unlocked a completely new way of looking at these infinite sums. By building that bridge from a discrete series to a continuous area, we've given ourselves a massive new tool for our calculus toolbox.
Really, the single biggest takeaway today is this connection. The integral test is what lets us jump between the world of summation and the world of integration. It gives us a way to use the tools we already know, like solving integrals, to answer these really deep, tricky questions about infinity.
But of course, the story doesn't end here. The integral test is fantastic, but it has that rule. The function has to be positive and decreasing. So what do you do if a series bounces back and forth between positive and negative? Or what about a crazy series that involves something like sine that just wiggles up and down forever? Our test won't work there. So what test would you use then? That is the next part of the adventure.